Alright, so for 4.3, we're learning how to graph a new function that we haven't quite learned about before. So today, we're learning about graphing radical functions. So far this year, we've touched or we reviewed how to graph linear functions. We talked about absolute value functions a little bit. And now we're talking about, and then we also talked about graphing um, polynomial functions. And then today is the day for radical functions. So, a radical function is anytime you have a radical and there's a variable that is underneath the radical. Okay, so anytime there's a variable underneath the radical, you'll get a radical function. So, radical functions can look different, much like x squared, or x cubed, or x to the fourth, x to the fifth. All these look different, and they're a little bit different, but they behave accordingly to whether or not the degree is even, or if the degree is odd, they look somewhat similar. So that's kind of the same thing with rational or radical functions, because these are inverse, like we talked about over the last couple of days, but radicals are the inverse of exponents. Um, so they behave somewhat in like a similar manner. So for the parent function of a square root function, this is f of x is equal to the square root of x. Okay. Now this is what it looks like. It starts here and goes out. So it starts at the point, the origin 0, 0, and moves out. So if you notice, it kind of looks similar in a way to the function y equals x squared. The function y equals x squared will look like this, though. Okay, like that. Now you notice that this graph right here is on its side, so it's almost like it's a half parabola, but then also rotated 90 degrees. So again, that should be because these are inverse functions. Also notice that the parent function of the absolute value function does not exist, so it's only half of it. So it doesn't go like this either. And the reason why that is, well, we'll actually talk about that later on in this lesson, and then we'll have a whole section about it in 4.5 or 4.6. But anyways, so let's talk about the domain and the range of this function. So the lowest possible x value, so if we're talking about the domain, the lowest possible x value is at x equals 0. And then you can see that the graph continues, the x values will increase from there. So the domain would be x is greater than or equal to 0. For the y value, it's the same thing. For the range, so you see the y values start at 0 and they're continually increasing like that. It's at a much slower rate than the x, but still increasing nonetheless. So y is greater than or equal to 0. And you can also write this in interval notation. You could say for both of them that it's from 0 to positive infinity. Now over on the right side is the parent function for the cube root function, which would be f of x is equal to the cube root of x. And this is what it looks like. And if we were to graph with it the graph y equals x cubed, that looks like this. So you see how that the cube root function is the same function rotated 90 degrees about the origin. And again, that's because these are inverses of each other. But the domain and range, so for the domain, you see that we're going to cover all real numbers, and same with with the domain we're going to cover all real numbers, and same with the range. So all real numbers. And then, of course, with just like any other graphing that we've done this year, we've also talked about transformations. So I think this chart should be nothing new for everybody in class. You should be pretty familiar with what a horizontal translation, vertical translation, reflection, horizontal or vertical stretch and shrinks should look like. Okay. Just to kind of cover it as to how it would look for a with a radical function, you can look in the examples here. So usually for a horizontal translation, if you're, say, for example, looking at a horizontal translation for a polynomial, that would look something like x plus or minus h squared, right? But for a radical function, it would look something like the square root of x plus or minus h. So that would be the difference. So usually we talk about how it's a horizontal translation if there's a plus or minus inside the parentheses. So the parentheses is the key. Now, there aren't any parentheses in a radical function, so it's anything that is underneath the radical. So that's how we determine whether or not it's a vertical or a horizontal change. And if it's underneath the radical, it's going to be a horizontal transformation. Now compare that with a vertical transformation, so like a vertical translation. So usually you would see for polynomials something like x squared plus or minus k. So with a radical, it would look more like the square root of x plus or minus k. So again, addition and subtraction is taking place outside of the radical, not inside. And for a reflection, so you can see it's over the y-axis if you're multiplying inside the radical with an x, with the negative, sorry. And then a reflection across the x-axis happens whenever you multiply by a negative outside of the radical function, of the radical. And then a horizontal stretch or shrink is when you use multiplication inside. So this would, if it were a polynomial function, it would be something like 2x squared or something like that. Or more generally, ax being squared. So again, parentheses is where you would make the distinction. So for a radical function, it would be the square root of ax. And then for a vertical transformation or a vertical stretch or shrinks, so if it were with a polynomial, it would be something like ax squared, where there are no parentheses. And then for a radical, it would be a x square root of x. So that's how you can make the distinction between a vertical and a horizontal stretch or shrink. And the same idea applies. So like if a for a shrink, this is when a for a horizontal shrink, so I guess I should write that. So for a horizontal shrink, a has to be greater than 1, and the factor will be 1 over a. For a stretch, so for a horizontal stretch, a would have to be less than 1, and the factor will be a. Now, that's the opposite with vertical. So vertical stretches or shrinks. So a vertical stretch is when a is greater than 1, and it's by this means it's by a factor of a. and then a vertical shrink, a has to be less than 1, and the factor is 1 over a. Okay. So that should be a good enough review and to show how it applies to radical functions. So here are some examples, so we'll go over some examples. For a and b, it wants us to graph these functions right here by using a table and then graphing. So we can go ahead and do that. So we'll use our table and make some inputs and outputs, okay? So we want to know the value of y when x is 0. So let's do the function f over here. So let's do f of 0. So if we plug that into this radical function, we get the square root of 1 divided by 4 times by 0. And as we do that, you should notice that we just get underneath the radical the square root of 0, which is just equal to 0. So when x is 0, y is also 0. Okay? Now let's try 4. So if we do f of 4, we get the square root of 1 divided by 4 times by 4, which is equal to the square root of 1, which is equal to 1. So when x is 4, y is 1. We can keep going. We can do f of 8. So that's equal to the square root of 1 over 4 times by 8. That's equal to the square root of 2. And when you do the math there, you should get something like 1.41 when you plug it into a calculator. And then for f of 12, this is equal to the square root of 1 over 4 times by 12. And that's equal to the square root of 3. Okay, now if you were to plug that into a calculator, you should get something like 1.75, I think. So 1.7, here, hold on, let me go ahead and punch that in. So if you plug that in, it should be 1.73. And now if you plug in 16, so f of 16, I guess I should write that over here, 1.73. And when you plug in 16, that's the square root of 1 over 4 times by 16, which is equal to the square root of 4, which is equal to 2. Alright, so if we were to graph out these points, so let me draw my x and my y axis. I'm going to draw my y axis over here, my x axis right here, because all of these numbers are positive. So my x and my y values are all positive. Now for my x axis, I range from 0 to 16. So I'm going to count by 2. So 2, I'll call this 4, 6, 8, 10, 12, 14, 16. For my y, I range from 0 to 2. So I'm going to count by halves. So 0.5 and 1, 1.5 and 2. So when x is 0, y is 0. So that should just be right there. When x is 4, y is 1. When x is 8, y is 1.41. So that should be something like right there. When x is 12, we get 1.73. So maybe about right here. And when x is 2, when x is 16, y is 2. So kind of try and connect the dots the best we can. We can see our radical function play out like that. Now the type of transformation here, of course, so we're multiplying inside. So that means it's going to be a horizontal stretch or a shrink. So if it's less than 1, so like right here, then this is going to be a stretch by a factor of the reciprocal. So this is going to be a horizontal stretch by 4. Okay. Now for B, just to save time, I'm going to just use the calculator. You guys can, if you guys want to pause the video, try it on your own, that'd be great. But to save time, I'm just going to plug in the values that I know that it is, that I've already done. So when x is -2, so remember that this is for g of x is equal to -3 cubed root of x. So when I plug -2 in here, I should get 3.78. When I plug in -1, I'll get 3. When I plug in 0, I get 0. When I plug in 1, I get -3. When I plug in 2, I get -3.78. So here I have both positive and negative x values, x and y values. So let me draw my x and my y axis so that they intersect in the middle. And I'm only ranging from, on the x, from -2 to 2. So I can call this 1 and this 2, this -1 and this -2. And on the y, I'll just keep the y as 1s. So when x is -2, I'm at positive 3.78. So 1, 2, 3, so pretty close to 4. So somewhere about right there. When x is -1, we're at 3, so 1, 2, 3. And then we're at 0, 0. When x is 1, we're at -3. And when x is 2, we're at -3.78. So the graph should look something like that between those x values. And there's a cube root function. Okay. Now it also wants us to state the domain and range. So the domain here would be that x is greater than or equal to 0, and the range here will also be y is greater than or equal to 0. And the domain and range of a cube root function would just be all real numbers. Okay. So that should be graphing radical functions. So that should be pretty good. Now for example 2, it gives us two different functions. So it wants us to describe the transformation from f to g, so from f to g, and then to graph them. So for a, let's describe the transformation. So this is a square root function. So I notice that inside we're subtracting 3. So underneath the radical, you could say. So underneath the radical, that should be a horizontal translation. So if it's minus, you go to the right. If it's positive, you go to the left. Here we have a minus, so we should be moving in the positive direction. So we'll say a horizontal translation. Right 3 units. Okay, and then we are adding 4, but that is outside of the square root, so it's not part of the radical. So if that's the case, that's going to be a vertical translation, but this time it will be up 4 units. So again, this is a cube root function, and we're moving to the right and then up. So I'm just going to draw my function, my x and my y axes in the just like that. So I know the parent function starts here, goes out like this. Okay. Now for a vertical so the transformations we said was 3 to the right. So I'm going to move this point right here 3 to the right and then up 4. So there should be something like right here. As always, you can make a table of inputs and outputs in order to know where the graph goes after this. Or if you are able to understand that this is a sideways parabola, or the top half of a sideways parabola, then basically you can just you can make you know what the outputs are going to be if you know it well enough. But that's generally what it should look like. Okay. So for B, so this is a cube root function. So from f to g, let's talk about some of the differences. So two differences I see is that we're multiplying by 8 inside, but we're also multiplying by a negative. Okay. So if we're multiplying by 8 inside, I know that's going to have to be a horizontal stretch or shrink because it's multiplication. And the value here is greater than 1. So that means that this is going to be a shrink by a factor of the reciprocal. So that's going to be a shrink by a factor of 1/8. So a horizontal shrink by 1/8. And then with the negative being inside, being multiplied by negative, so that's going to be right here a reflection in the y-axis. So reflection in the y-axis. Okay, so it's a cube root function, so I'm just going to draw my y-axis here, my x-axis right here. Okay, so I know that the parent function, as we talked about before, looks something like this. Alright, now the transformation say is going to be reflection over the y-axis. So that's one, but then it's also going to be a horizontal shrink. So that means horizontally it's going to be squished. So that should look something more like this right here. You see that the graph, a lot of the values are more closer to the y-axis. So again, it's like it's compressing into the y-axis. Okay. So that's transformations, applying the transformations, describing them. Now let's jump to example 4 here, where we're going to write the transformation as it's given to us, as it describes it to us. So for example 4, it says that f of x is equal to the cube root of x. So we want to write a graph, we want to write a rule for g, so we're going to write something for g of x. Okay, so the first thing it tells us is that it's a horizontal shrink by a factor of 1/6. Okay, so a horizontal shrink by a factor of 1/6. So if we have a horizontal shrink by a factor of 1/6, that means we're going to multiply inside by the reciprocal of the factor. So this means this is going to be equal to f of 6x. We're multiplying inside by the reciprocal. Okay, so this would look like, knowing what f of x looks like, this means we're going to replace x with 6x. So we have the cube root of, and instead of x, it's going to be 6x. Okay. Now, after that, it says the transformation is followed by a translation 3 units to the left. So that's a horizontal translation, which means inside, if it's to the left, that means it's going to be adding inside. So then we're going to do g of x is equal to f of x plus 3. So we're going to input x plus 3 into our new function. So we have the cube root of 6, and instead of x, we're writing in x plus 3. And we can simplify this by distributing the 6 in there. So the cube root of 6x plus 18. Alright, and that should be it. So this is the rule of g of x. That's our new g of x. Alright, so for example 5 and example 6, for these examples, we're going to use a calculator to help us. So first, to graph, if we're going to use a calculator to graph this function right here, the thing is we have to make sure that y is by itself, because our graphing calculators are we can only graph if y is by itself, if we have y in terms of x. So we have to solve for y. So if I have 1 over 2 y squared equal to x, if I want to get y by itself, first thing I'll probably want to do is multiply both sides by 2. By doing so, I can get rid of that right there, so I have y squared is equal to 2x. Alright, now to get y by itself, I have to take the square root of it. I'll take the square root of both sides then. So when I do that, the radical and the exponent cancel, so I'm just left with y. And this is equal to, now remember, if you take the square root of something, you have to include both positive and negative values of it. So I get plus or minus the square root of 2x. Okay, so I actually have two different answers. I have y is equal to the square root of 2x, and then y is equal to negative square root of 2x. Alright, so let's think about why we might have possibly gotten two answers here, and why that might make sense. So I'll pull up my calculator. Alright, so first thing I have is y is equal to 2 square root of 2x. So square root of 2x. Okay, when I graph that, you can see that this is what it looks like. So that looks like a radical function, right? That's a typical radical function. Now this is like the same function, this is like this radical function up above it, but we're multiplying by a negative outside, which means we're going to have a reflection. It's going to be this same function, but reflected over the y-axis. Okay, so let's go back to my graph. And now I'm going to negative square root of 2x and graph it. So there you go. So you see how this is a sideways parabola. Now, if we go back up here to the beginning, remember how we talked about this before, notice how we don't include this bottom half of this graph right here, because a parabola is a U-shaped. So whenever we flip it, we can't draw the bottom half of this function. And the reason why we can't draw it or include it in this function is because if we were to do this, this ceases to be a function. Because a function by definition says that for every input value, so for every x value, there is only one y value. But if we were to include the bottom half, see how we have two y values for the x. So in other words, this fails, if you guys remember, the vertical line test. Okay, so that is why we write the square root of x and negative square root of x as two different functions if we were to graph this as a sideways parabola. They have to be graphed as two different functions. Alright, now for example 6, for example 5, if we were to identify the vertex would be in the same location at 0, 0, and the direction that the parabola opens to the right. Alright, now for example 6, this is actually pretty cool because this helps us to graph circles. Now, we're going to use a graphing calculator, but again, we have to make sure that we solve for y, or else we can't input it into the graphing calculator. So to graph for y, I need to get y by itself. So I'm going to subtract x squared from both sides. Here they'll cancel, and I'll be left with y squared equal to 16 minus x squared. And now I can take the square root of both sides, remembering that I get both positive and negative when I take the square root. So I get plus or minus the square root of 16 minus x squared. So this is going to be the square root of 16 minus x squared, and negative square root of 16 minus x squared. Okay, so let's graph these functions. Alright, so I have the square root of 16 minus x squared. And if I were to graph that right there, that's what it's going to look like. Now let me correct my scaling here so that this is just 1, and now let me graph that. Oops. So I did the wrong one, so 10 to negative 1. Something's up with this, probably because I have my iPad tilt horizontally. But what if I were to, I guess, make the scaling by 4? Anyways, so you see that this is by 4, so 1, 2, 3, 4. And then I also need to graph the lower half of that. So this is going to be square root of, oh whoops, I need to include the negative. So negative square root of 16 minus x squared. And when I graph that, I'll get the bottom half of the circle. Okay, so that's how you can graph circles, is by, this is typically what a circle equation looks like, and then if you solve for y, you'll get two different functions, which allows you to graph the circle. The center of the circle is at 0, 0, and the radius is going to be 4, which happens to be the square root of 16. Okay, so the radius is going to be 4, and the intercepts are at x equals plus or minus 4, because if the center is at 0, 0, then that means it will go out to both positive and negative 4. Okay, so the rest of this is just extra practice for you guys to do. I'm probably not going to go over it anymore in the video, but it would be useful to get a little bit more practice, and I would highly recommend that you do. If you have any questions on the extra practice problems, just send me an email, or just send me an email about the homework. So that should do it for this video. Thanks, guys.